Valeu.
Okay, so my name is Stefan from Walker University. And we give, of course, the introduction to Lorentzian.
Thank you very much for the introduction. Thank you very much for the invitation and organizing this beautiful workshop. One technical question, can we turn this down a little? Yeah, can I just turn it off?
Ele quer desligar lá com os dados.
Just press the button. This one?
But we can lower
Yeah. No, that's not the problem.
25.
Acho que se puder desligar, acho que ele está querendo desligar. Não, se você puder ajudar lá. Stefan.
Yeah? Let's go. So, yeah, introduction to Lorentzian geometry. So, this is a bit out of line here, because it is not per se Weber electrodynamics and not symplectic geometry. Even, of course, I mean, it's you can interpret every differentiable geometric system as an Hamiltonian system by itself. But Joa told me that in certain areas of Weber dynamics, Lorentzian geometry is naturally. So that's going to give you a bit of an idea how geometers like myself look at this. Yeah? And for that matter, I don't assume that too many people have been exposed to much Lorentzian geometry, so I will focus more on the differences between Riemannian and Lorentzian geometry. So I assume that sort of everybody has seen a course in differential geometry, and then there have been defined Riemannian metrics, geodesics, and curvature. Okay? So I assume some familiarity, even though if you don't see something that you have not heard, you just ask me and try to explain. So, to start things off, let me just give you the formal definition, which of course is very mean of me, and then discuss examples to illustrate what it means and what are the classical examples of Lorentzian metrics. Yeah? So we look at M be a smooth manifold, and in contrast to symplectic and Riemannian geometry, this will mostly be non-compact. And a tensor field usually denoted by G, and this is a section of the O2 tensor bundle, which just means it's a bilinear form on every tangent space, just like that, is a Lorentzian metric. So if GP is non-degenerate, we've seen that already today in the form of the symplectic forms. It is symmetric. That, of course, is in contrast with the symplectic forms. Non-degenerate, symmetric, and the index of every GP is 1. So GP is just simply evaluating this bilinear form at a particular point, or looking at a particular bilinear form in one tangent space. Symmetric for all P and M. And this, of course, means that I assume that GP is always isometric to the diagonal form with 1 minus and the rest are positive eigenvalues. Yeah? I have no particular opinion on this, it's just as I learned it. You know? In physics, often this is reversed, that you look at 1 positive eigenvalue and n minus 1 negative eigenvalues. But for me, coming from Riemannian geometry, I want that on a space like this is a Riemannian metric. It's just a matter of taste, there's nothing deep behind that. Okay, so that's the formal definition, yeah? Just for, as mathematicians work, we give formal definitions. The remark, of course, as I already said. The first one is every tangent space of this thing is always isometric as a, what did I do here? It's always isometric to a pseudo-Euclidean space, which is just Rn, and n is always a dimension of m. This is one of the contradictions of mathematics or differential geometry, that m is dimension n. With the usual inner product, just brackets with a subscript 1, where this is just simply minus d0 squared plus the sum of dx I squared. Yeah, this is what's called Minkowski space. Will already be, so say, the first example we will see of the Lorentzian manifold. So what did I want to say? So what is the usual picture you encounter in the textbooks of this space? Is what distinguishes it from a Euclidean vector space, where this minus here is a 1, is the locus of vectors whose inner product is equal to 0, which is a projective variety. And here it's a double, it's basically a cone, and the projective variety is just a sphere. So this is what in Lorentzian geometry would be called the light cone. And how do I say this best way? This is the reason for its relevance from physics for this geometry is the existence of a speed limit in general relativity. So the reason for this existence, the physical reason, let's put it this way, or intuitive reason, is the speed limit in relativity. So what is the idea here? The idea is already appearing in Newtonian physics. So what you can look at your physical space, you can dissect it into space, which is just simply the points in your space with coordinates, and you add one axis, which is just time. In Newtonian physics, there's absolutely no reason to look at it this way, because it doesn't make any difference. But in relativity, you say that nothing can be faster than the speed of light. That what that basically, this assumption does for you, it limits the angle of your velocity vector for a unit amount of time to a certain angle, to keep a certain angle with the rest space. Yeah? So this angle here, theta, has a limit from below. And what is a limit from below on such an angle is nothing but prescribing a sort of cone to which all speeds of particles are confined. That's where basically the cone fields in Lorentzian geometry, or why in the relativity these cone fields appear. That they are actually round cones has something to do with spatial isotropy, that basically space should look in every direction the same. And that, on top of that, if you look at deeper into physical reasoning, then this bilinear form will appear as a form of measurement of energy. But just from the very basic why such cones should appear, or why the bilinear form to measure things in Lorentzian geometry or relativity is not a Euclidean inner product, can be more or less derived from the fact that we are looking at things that have a speed limit. Okay. Okay. So that, yes. What did I want to say here as well? Okay. Yes. So examples. So you've seen already the first one, yeah? The zeroth example is Minkowski space. That is always the thing, just like in symplectic geometry, the zeroth example is R2n with the standard symplectic form, no Cn. Okay. And the next one, what you derive from Minkowski space is so-called de Sitter space, which is nothing but those points in, usually denote this is Rn1 subscript, just indicating the index of the bilinear form, is those points in Rn plus 1n. I want this to be n-dimensional de Sitter space, such that the inner product of those points is equal to 1. The picture here is you have this double cone, and around, I have colored short. And around that thing, you have such a body. This is exactly de Sitter space. In this case, here, de Sitter space. And the funny thing about that thing is, we will see later, this is the sectional curvature of this is constant to 1. Just like in Euclidean geometry, that the unit sphere in Euclidean space is the space of constant curvature. And you can actually give this also a radius, then you would call this R squared and this for R positive. Yeah. Of course, for R equals to 0, it's a double cone, which is not a smooth manifold.
Yes, of course, the Sitter space is this hyperboloid with the metric element.
Oh, with the metric, of course, induced, yeah? Yeah, with the induced metric.
That's like a Riemannian metric in this case, or not?
No.
No?
Induced Lorentzian metric. That's the thing. If you look, metric. Side remark, if you look at the points x and r n plus 1, 1, such that the inner product of x with itself is minus 1, and let's say that the 0th coordinate is positive, then you get nothing but hyperbolic n space with the induced metric from the Lorentzian metric. Here the induced metric is to Riemannian, and here is Lorentzian.
Oh, I see. The other one is the
Exactly, that's the
parting side. The component, yes.
the Lorentz model of hyperbolic space. Basically what happens is, since you're writing down here minus 1, you're killing off the negative eigenvalue.
I understand what.
Here, in the other one, you're losing just one positive one. Okay. So, and of course, if you have curvature positive, then you also have negative curvature. But you don't find those spaces in Lorentzian space, but you have to go one index higher, which is anti-de Sitter space, which is usually called ADS, n of radius r, which is nothing but x in Rn plus 1 with index 2, so now you need 2 negative eigenvalues, because if you kill one, you still need to retain 1 negative eigenvalue, which is nothing but those inner products which are minus r squared. And the Sitter 2 space, I would draw the same picture, because if I flip the Lorentzian metric in dimension 2, so I just multiply this thing with minus, I have an inner product with index 2. Then the Sitter space turns into anti-de Sitter space. Just the sectional curvatures are reversed. So this has constant sectional curvature r, 1 over r squared, and this has sectional curvature minus 1 over r squared. And one interesting thing you might have encountered in your life before is that anti-de Sitter space of 3 dimensions is nothing but the special linear group over the reals with its killing form. Because, well, sorry, de Sitter space. I always get this wrong. Because if you have a matrix A, B, C, D, then the determinant being equal to 1 is nothing of this matrix A, B, C, D is nothing but A times D minus C times B. And despite its look, that's a symmetric bilinear form of index 2.
The subindex 2 means 2 negative.
Yes. So maybe just for notation here, it will not appear so often, but just for the shorthand. Yeah. Rn is nothing but Rn with the inner product, symmetric inner product of index k, where this thing is defined as minus dxi squared from I to 1 to k plus the inner product from I k plus 1 to n of dxi squared. Yeah, so basically just count the number of negative values. Okay, so these are, so Minkowski space, of course, is the space of sectional curvatures vanishing, yeah? Unique, simply connected. The universal cover of these two are the unique spaces, simply connected spaces of sectional curvature, positive and negative. From the physics point of view, that is, of course, not terribly interesting, even though there are applications of this. Maybe I should say this. I will not solve the Einstein equations in this lecture course. I will rather concentrate on geometric features of a given Lorentzian metric. Yeah? Since people here, I assume, are mostly interested in dynamical questions of geodesics and things like that. So I will rather concentrate on these phenomena than on how to construct special sort of Lorentzian metrics. But of course, the examples I will give you are somehow motivated by the Einstein equations. So the second, now maybe more relevant to physics example, are the Robertson-Walker spacetimes. What are they? Well, we take, and that's maybe one basic recipe of how to construct Lorentzian metrics, besides this, is we look at a Riemannian manifold sigma k, where k is a Riemannian metric, be a Riemannian manifold, and from the get-go here for these examples, I will assume of constant sectional curvature. So basically there are portions of hyperbolic space or flat tori or spheres. Yeah? Curvature plus minus 1 or 0. Yeah? So I won't make too much variation. And f, I look at a positive valued function of some interval I, which is smooth. So I is an open interval of the real line. Yeah? And then I look at the following manifold MKF, which is nothing but the product of I times sigma with the following metric. I look at minus dt squared plus f of t times k. So basically what that is nothing but I take the real line, and across I scale a certain a certain Riemannian metric with time. Individually, they all these sigma is a sigma t1 and there's a sigma t2. Yeah? So this t2 and here's t1. They're all individually they're all the same, basically up to constant factor. They're all the same Riemannian manifolds here. These hypersurfaces in here but as time evolves, the universe contracts or expands. That's basically the idea. This construction here is called a warped product, if you've ever come across such things. A very popular mode of constructing. What's its purpose in physics? It is the simplest model for the entire universe. So if you look at cosmological models, and you make some simplifying assumptions, for example, one of those is the principle that universe on large scales looks everywhere the same, so matter is evenly distributed. That is where this enters here. And the function then is determined by if you assume that the universe is expanding or contracting. So that's, as I said, let me write this down. Isotropy of matter, that matter distribution, that leads to constant curvature of the hypersurfaces, constant curvature on sigma, and I forgot the quotes here. And then write the Einstein field equation at least down once.
But the sign of the curvature is related also to the distribution of mass, or?
No, that's an experimental thing to determine. And there has been experiments, and the current state of opinion is that we are almost flat. So yeah, let me see. So the Einstein equations here in this case will be 1 over 8 pi, the Ricci curvature of the metric G here, minus 1/2 the scalar curvature of G times G should be the rho times plus P. Then must be, yeah, that is dt, tensor dt, plus, what did I forget, times P times G. Yeah. This is what basically these physical assumptions imply, and then if you make these assumptions here, then you get a certain form of this. Okay. To connect this back to the first examples, you can write the zitter space as such an inner product, as such a walk product, sorry, where in this case sigma k is nothing but the sphere with the canonical round metric, yeah, so just basically this waist here. And the warping function, this f, is nothing but, let me get, I always get this wrong, is t goes to square root of 1 plus t squared, which is nothing but the unit speed parameterization of this vertical geodesics here. Okay, that is Robertson-Walker. So for the big picture, if you want to go a bit into details, or a bit closer to certain particular objects, then the first non-trivial solution to Einstein's equation of vacuum is the so-called Schwarzschild metric, which just models a point mass in non-rotating resting point mass in space. Yeah? And the funny thing is that I will write down the metric. Interestingly, I think Schwarzschild wrote it already down the year Einstein wrote down the Einstein field equations, instantly. saw that. So what is just the formal definition before I discuss? So you look at the following space. You take R times R3, and for mathematicians, you have to exclude the zero and the unit sphere. Usually in physics books, the unit sphere is not excluded, but for the particular standard coordinates, you write down the usual cylindrical coordinates on R4 here. You have to exclude because they're the metric that's defined in these coordinates. Okay, this is nothing but, let's see, yeah. This has two regions, two connected components. Let me see, a longer piece of chalk. This is R times 0, 1 times S2. Disjoint union with R times 1 infinity times S2, where, of course, these are, so I take polar coordinates on R3, patch them up to cylindrical coordinates on R4, and then and in these these cylindrical coordinates, the Schwarzschild solution is nothing but minus 1 over minus R. That's where you see where this, here you don't see. But here you will see it, that is because that is exactly 1 over this function, dr squared plus r squared. And here you just take the usual round metric on S2. So basically what the Schwarzschild thing does is it rescales time and radius with the inverses of one function, and the rest, the radial part, looks like a Euclidean space. Okay, that's the metric, and it is actually, well, you can derive it ad hoc as a spherical symmetric static solution to the Einstein equations. But there are actually uniqueness theorems. So what is the purpose of it is actually model of a non-rotating massive body, or non-rotating Dirac mass. That is actually sitting at 0. Yeah, because there.
It's also curious, this statement is no rotating point mass, right? Because what's the meaning of a rotating point?
Well, because there is a rotating point mass solution as well.
So what's the angular momentum of a point mass? How do they define that? The moment of inertia.
Well, maybe I should not have said non-rotating. Rotating here, non-rotating is meant in the sense of staticness. And static means in this context that the time direction is a killing vector field of the metric whose orthogonal complement is integrable. In that sense, it's non-rotating. It's non-rotating in a
So it does not mean that there is no momentum.
exactly, there's no angular momentum.
There's no spin.
Yes. But in mathematical terms, you would say that the orthogonal complement is integrable.
Because in quantum mechanics there are points
With the spin, but
that
not here.
that have spin.
Yeah.
There is the difference.
Yeah.
A non-rotating Dirac mass is a mass without spin. Rotating point mass, I think, there is like electron at point with spin.
Okay.
I'm sorry.
No. I'm always very, very careful with making physics statements.
I think.
But it also makes mathematical sense
Yeah.
in terms of these killing vectors. And if you let go of the assumption that the orthogonal complement of the t direction is integrable, you end up with the so-called Kerr solutions. And these are actually point masses that are rotating. But the metric then looks very, very complicated. But if you let the angular momentum go to 0, or that you assume that the Killing vector field, the orthogonal complement, is again integrable, you end up with the Schwarzschild solution. Yeah. So this is actually, Schwarzschild metric is part of a bigger class of solutions to the Hansen equations. Okay, so let me write down a theorem for you, which is actually pretty recent. There are a lot of theorems that saying that Schwarzschild is under certain assumptions unique solutions to the Hansen equations. But I find this a very geometric formulation of one of these uniqueness theorems, and it's, you see it's from 2015. So if you assume you have a metric on r times r3 minus a certain ball of radius capital R, and a Lorentzian metric on there. If this thing is one Ricci flat, which just means the Ricci curvature of the metric vanishes, which is always, that's the way for relativists to say that it's a vacuum solution. It is static, which means, as I said already verbally, as I already said, that dt is killing, meaning that the flow generates isometries, and dt orthogonal is integrable. Okay, that means static, and the third condition is geodesically complete at infinity. That is supposed to be, that needs an explanation what that means. That means all geodesics, all geodesics either intersect the boundary of the cylinder above this ball of radius r. So basically, let me give you the geometric meaning of that. Either that happens, or they are complete, or are complete. When I say as a geometer, a geodesic is complete, that just means the affine parameterization is defined for all the values. Then this thing here is isometric to a piece of Schwarzschild, a piece of Schwarzschild. Because I could just delete from this part here just a bigger piece and have the same assumptions. So it cannot. Plus the radius here of this thing. Yeah, here's the massive one. Okay, so why is this dichotomy here? What is this good for? This r times S2. The usual picture you would draw. Talk about Schwarzschild. Is you have the central axis, which is forbidden. Yeah. Then around you have the cylinder. Of course, I'm deleting one dimension here. This is r times 1 times S2 here. This is called the event horizon. Yeah? And if you look at the light cone distribution, the way these cones are before, as I said, what they would look like on the boundary. Formally, the metric is not defined on the boundary, But if I multiply by this metric by these functions, I will not change the cones at each point, but then at least the metric will not degenerate or will not go to will be well defined on the boundary here. So what happens here on the boundary is that these cones are tangent to this manifold here. Yeah? There's one direction, the dt direction, which is normal. Okay. So, and if you remember that, as I said, R to infinity, this goes to the usual Minkowski metric, and in here, the funny thing, which in physics usually is not discussed, but then the R direction becomes the time directions, and the T becomes the space direction. The sign change. But if you remember what I said before, that the only allowed directions for particles to travel are in the directions of the cones, means that every particle that passes through here stays inside the cylinder, never gets back out. So everything that falls into the black hole, also called this the black hole, never gets back out.
So geodesics in this context, more or less like this geodesics in this context.
Yeah.
You have UN geometry minimize the length between 2 points. Is there any interpretation of that?
There's a story. I will come to that. Yeah. Basically, I can maybe give a primer. You have to look at certain classes of geodesics. Basically, all this minimization and extremality things only make sense for the causal geodesics, the ones that point inside the cones. Outside is meaningless. It's actually more like the Hamiltonian action function. But I will come to that in detail. Okay. What else I want? Yes. After this. So. So I already said that from a certain point of view, you can ignore the singularity on the S2. This is not so physicists talk as it might seem, but you can actually change coordinates so that both things fit together finally. Yeah? So when you look into textbooks on GR, they would say, well, what happens here is a coordinate singularity, not a curvature singularity. The metric is extendable as a C2 metric. It cannot be extended as an analytic metric because this is an analytic expression, so you cannot. Analytic functions cannot diverge if they agree on an open set. But as a C2 metric, you can join these things together. So both regions can be joined. What did I say? In the Kruskal coordinates. What are they? Well, you consider the following function, f of r, which is nothing but, if I'm not mistaken, r minus 1 e to the power r minus 1. And you look at g of t, which is nothing but e to the power t. And then you map this pair tr, these coordinates here, this and this coordinate, you map to a pair uv, where these are implicitly defined. U times v is supposed to be f of r, and the quotient v over u is g of t. And this maps basically fixing the angle in this S2 gives you a half plane. Maps this thing times 0, 1, union 1, infinity, with the induced metric, which is nothing but minus 1 over r dt squared plus 1 over r dr squared to what? Write this down quick here. Isometrically. Onto, well, r times 0 infinity with the metric 8 over r of uv. Now you consider this function r, this radius r as a function of uv times e to the 1 over r of uv times du dv, where this is just a short Lorentzian geometer shorthand for the symmetric tensor product of du dv. This is just another matter, another way to write down the Lorentzian inner product in 2 dimensions. So what is this related to? If you take the usual coordinates, you have x and y. You have the usual cones at angles 45 degrees. Here the inner product is, doesn't matter the sign, it's minus dx squared plus dy squared. And if you rotate your coordinate system by 45 degrees, you get exactly this. So if you say this is u, and this is v, then this is the same thing as saying this is du dv. Okay. And if you, let me write this over here. If you remember that there was an S2 to the picture, then you just, on that part you don't do anything, but you get the Kruskal space-time. Which is nothing but, well, this thing what I wrote down here, r times 0 infinity times S2 with the metric, the one I already wrote down, 8 over r uv. Remember here there's a, remember which one, times this factor, r uv times du dv plus r squared. This is the same r, yeah? G0. Basically what this does with this picture here is in this plane you have the r equal 1 line here, and the other ones, the outside and the inside, they are symmetrically. This is r equal constant bigger than 1, and this is r smaller than 1. These lines here just have a bond against it. So in this metric you can cross the event horizon. So basically time will look in this direction. Okay. So that's for the classical solutions. They are motivated mostly, I mean, if you ask a mathematician, they would never come up with this metric. Yeah? For a geometer, let's say. Yeah? This is motivated by considerations in physics. But what is always important in relativity is, at least as a model, that things are flat, at least Ricci flat. And Ricci, because it models vacuum spacetimes. You would say, probably from the get-go, why look at the boring objects, at the empty universes? Well, the Ricci flat metrics are already a difficult subject. So if you cannot control the easy examples, then you should maybe not look at the complicated examples. So start with the easy. trivial problem, of the trivial looking problems. But Ricci flatness in itself, as I said, is already difficult. So you can even go one further and look at the flat spacetimes. And when you, as a Riemannian geometer, if you look at flat spacetime, you would say, I mean, now it has to be easy. Yeah? And in a certain way, it is actually easy, but in other ways not, because I can give you the following simple example. It's called so-called Misner spacetime. It has a certain funny behavior you will not expect when you know Riemannian geometry, and especially Riemannian geometry of flat manifolds. So we look at those, what did I write? Tx in R21, two-dimensional space, such that x minus t is smaller than 0. I'll call this n bar. So if I make a drawing, if I'm not mistaken myself, I usually have problems. I look at this half space. This is n bar. In this two-dimensional Minkowski space. Okay, and then I take a certain quotient of this thing. For theta, should be positive, but it doesn't matter very much, it could also be negative. Fix the hyperbolic rotation. Just write down the matrix. It's cosine hyperbolic theta, sine hyperbolic theta, sine hyperbolic theta, cosine hyperbolic theta. These are, you know those things from hyperbolic geometry. Yeah? And look at the hyperbolic rotation, and it's and the group generated by it, and the group gamma, which is nothing but z, yeah, generated by it. So this actually, on this open half space, this group gamma operates freely and properly discontinuously. So you can take a quotient. Yeah? And maybe I'll make another drawing. Let me give you a better picture of this. So you have this half space, 45 degrees. There's here's the 0 of R2. There emanates another line of vectors of length 0 in the Minkowski inner product. And then you have one of these hyperbola, are basically vectors of length, of negative length, and then you have the ones of positive length. And since we're in R2, they're all one-dimensional, so they're all the same. Yeah? And this hyperbolic rotation here sends nothing but a point on this here by a certain distance to this point here. Maybe I should give that a name, d theta. So this is d theta here. And yeah, d theta. And the same thing happens over here. There's one point here that is sent by d theta to this point. And on this line here, there it's nothing but an exponential multiplication, multiplication by constant factor. If you restrict this to the line of 45 degrees, this thing here is just multiplication by constant. Okay? So this generated by, so gamma operates freely and properly discontinuously on n bar, and the spacetime I'm looking at is just the quotient of that thing. So the quotient of m bar by gamma is it's nothing but a cylinder, so it's S1 times R. These curves here are all closed, these hyperbolic pieces plus this piece of this light cone thing. This is thing, and the induced, or let's put it this way, the induced flat metric is geodesically incomplete. In a peculiar way, incomplete. In a very peculiar way, because if you look at, for example, this light-like geodesic here, this will be incomplete. Since it comes from Minkowski space, it's just an affine line. And of course, the affine line has to end here at a certain value. Yeah? But in the quotient, this thing is a closed curve. So you have a cylinder, there's a closed curve sitting on that, which is a geodesic, and it's a light-like geodesic. But if you traverse this closed curve, you start accelerating and exponentially fast. And in finite time, this thing accelerates to infinite speed. So it is an incomplete geodesic that does not leave a compact set of the space-time, of the underlying manifold. If you come from Riemannian geometry, you would expect that geodesic incompleteness has something to do with the curve leaving every compact subset of the base space. In Lorentzian geometry, is not sure. Of course, incompleteness always has to do something with leaving every compact set of your of the phase space. But here, the compact sets of phase space you leave are in the tension spaces above. Yeah? That has something to do with the fact that the not the unit tension bundle, but the set of vectors of length 0 is non-compact in the Lorentzian manifold. Okay. I wanted to give you precise coordinates on this thing. Yeah? So if I have coordinates phi s, then the metric here, the quotient metric is minus ds d phi plus s d phi squared. If you want, you can look at the usual coordinates. They are 2 times square root minus s cosine hyperbolic of phi over 2, and x is 2 sine hyperbolic of phi over 2. So what happens here is these light cones, they lie on this thing, and here they are above, and here they are here. Which is another interesting thing, for example, for that matter. Such behavior, there's a path of particles which is going in circles here. So this thing below this closed line, like there's an actual time machine in this thing. And physicists, of course, they don't like that, yeah? These causality violations, because then you kill your own grandfather and so on and so forth. But the message here on this metric is that just the assumption that your spacetime is empty does not imply these physically reasonable assumptions like causality. So this is another matter. These global assumptions on the structure of the dynamics that do not necessarily come from assumptions on the curvature. Because when you look at the Einstein equations, they merely say, for example, in the vacuum case, Ricci curvature is 0. But as a physicist, you would say that should be enough to determine that the universe has some meaningful structure. For example, it does not emit any time machines. But that is simply not true, by example. Okay. So what did I say? I have not given any proof so far. I just talked about it. Maybe something more adhering to mathematicians, or especially mathematicians coming from dynamical systems, is of course the question of compact Lorentzian manifolds. And so in Riemannian geometry, it's a classical, or one of the basic results, that every manifold has a Riemannian metric. So this is absolutely no condition. Assume that there's a Riemannian manifold in any particular smooth space. But in the Lorentzian case, this is actually a condition. It is not a condition for the non-compact ones, but for the compact ones it is. Right? So let M be a closed manifold. And I say closed, I mean compact without boundary. So then M admits a Lorentzian metric if and only if the Euler characteristic of M vanishes. So that's an actual topological condition. For example, the two-sphere does not have a Lorentzian metric. So an idea of proof is well, if you have a Lorentzian metric, so first of all, first step is define locally what you can do. Define locally vector fields X over some open set U, which you can, with the property that the inner product of these vector fields with the Lorentzian metric is negative. So you assume you have that M admits a Lorentzian metric, and then we want to show that the Euler characteristic is zero, it vanishes. And then what you can do is you can take a partition of unity, subordinate to such a covering by such open sets, and just add up these vector fields with this partition of unity. Since it's a partition of unity, it's at every point it's basically a convex combination of these vector fields. But of course, these vector fields could be in opposite parts of the double cone. Right? In every tangent space, you have this double cone, and one x1 could be up here, and the other one could point exactly the opposite cone. If you add them up with a convex combination, you could end up at zero if you get unlucky. But we want, in order to arrive at vanishing Euler characteristic, I need not necessarily a non-vanishing vector field, but a section of the projective bundle. But projectively, these things are like basically the same convex subset of RP, of the projective space of these tangent spaces. So if I do this adding up procedure in the projective space, which is of course a bit, I have to give meaning to that, but you could do that, then you can construct from such a local from these locally defined vector fields and the partition of unity, you can construct a section of the projective contour. Gluing or adding via a partition of unity yields a section of the projective tangent bundle. And that is known to be equivalent to the vanishing of the Euler characteristic. Okay, and the other way around is basically employs the same strategy. if you know that the Euler characteristic vanishes, then you have a section of the projective bundle. If this Euler characteristic is 0, you have a section of the projective tangent bundle, then let H be a Riemannian metric on M, and choose, you might not be able to lift this to a vector field, but you can lift it up to a vector field modulo sign. So you can choose H unit length representative of this thing up to sign. Yeah? And choose at every point, a H unit length representative of S at this point. Every point P of SP. And I call this maybe XP. And then you define a Lorentzian metric G as simply minus D minus 2 XP unit dual. You just take the dual vector to this vector field plus H. This is Lorentzian. And this ambiguity with the sign goes away here because I have this twice. Yeah? If I multiply this with minus 1, then this gives the same end. And since I wrote down here, since this thing is unit length and I wrote down here a 2, this actually has index 1. This is a non-degenerate bilinear form symmetric and an index 1. So that's how you get Lorentzian. Okay.
Stefan, how many time you need?
Oh, sorry. I thought I was.
From my point of view,
No. Let me. Did I already say it? No, let me stop here and I make a remark on Thursday. Yeah. Repeat this.
Okay, that's.
Oh, sorry, I completely forgot.
Any questions?
This was usually this odd dimensional compact manifolds. They always have.
Oh yeah.
So it's more or less an odd dimensional in the compact setting.
Yes.
Usually you have odd dimensional.
Yes. So the argument is always the Euler characteristic is the alternating sum over the Betti numbers. And for in odd dimensions, this is of course it's an even sum, so it is 0 by Poincare duality, and that's why you always have in the odd dimensional case you have always a Lorentzian metric. And in the even dimensional case, it's.
Okay, any further questions? Then let's sing our speech. Tomorrow morning, he said.